In this section, we're going to cover one of the most fundamental relationships in factory operations, or we could say in the science of lean. And this relationship is called Little's Law. Our learning objectives are to understand Little's Law, which is the relationship between inventory, flow rate, and flow time, written as I equals R times T. And given two of these parameters, we want you to be able to calculate the third parameter. And we want you to be able to understand and discuss the significance of Little's Law for lean production, and in particular, how increasing inventory increases flow time. Little's Law is named after Professor John D. Little, the MIT professor who formed and first used the law in 1954 and then proved it in 1961. His law stated in the original paper that the average number of customers in a system over some time interval is equal to their average arrival rate multiplied by their average time in the system. We're going to use the following terminology. I is equal to inventory. R is equal to the throughput rate or flow rate. So this is the rate of production. And T is the flow time, the time it takes a product or service to be performed. Now we're calling this flow time. In other texts, we'll use the word lead time or cycle time, but we want to make a point here that we are not using lead time and cycle time to mean flow time. In fact, for us, they mean something different. So please, for this course, flow time is our T, the time it takes a flow unit to complete a process. And this is the terminology used by the textbooks by Professors Cachon and Terwitsch. Little's Law then is given as inventory equals rate times time. Very simple. I equals RT. Now let's look at how this works. Here we have t-shirt production. First we have raw materials, so different colored fabrics, and we have this inserted, so some kind of insertion process into a textile cutting machine, which is here represented by our scissors. This machine then cuts out the pattern and they're sewn together. So we have 3 steps: insert, 3 minutes per t-shirt, cut, 3 minutes per t-shirt, and sew at 6 minutes per t-shirt. Let you guys do this yourselves. Where's our bottleneck? You've got it. 6 minutes per t-shirt at sew. This means P is equal to 6. Our process capacity is equal to our bottleneck capacity. Is equal to 1 over P, right? Which is 1 over 6. And then we want to multiply that by 60 minutes per hour. And we end up with 10 t-shirts per hour. That's our process capacity. And here we assume we have enough material here and we have a lot of demand. This is equal to our rate of production. R, 10 t-shirts per hour. Now what's our flow time here? Again, for you guys, what's our flow time? The time it takes our product or our service to be produced, we have here 3 plus 3 plus 6. We have equal to 12 minutes, right? So 12 minutes, maybe we can convert that also. We have 1 hour for 60 minutes. 12 minutes is equal to 0.2 hours. So rate is equal to 10 and flow time, or T, is equal to 0.2 hours. What about inventory? So here we have this again, 10 t-shirts per hour, 0.2 hours. I equals RT. R times T by Little's Law. We end up with 10 t-shirts per hour times 0.2 hours. And we get 2 t-shirts. Now what does this mean? Well, for our bottleneck rate of 10 t-shirts per hour and for a flow time of 12 minutes, which is here the fastest it can be, you need to have 2 t-shirts on average in your system. Now, thinking about this, the bottleneck, as we know it, has to be working all the time. So we have to have 1 t-shirt sitting here at so, all the time being worked on. And then we need to have another t-shirt in our system, t-shirt 2, which is being shared between insert and cut. Now, of course, that doesn't mean that we slice our t-shirt in half, right? And we insert half of a t-shirt for the 6 minutes that sew's working and we cut it for the 6 minutes. No, it means during this 6-minute period, 3 minutes will be inserting t-shirt 2 and 3 minutes will be cutting t-shirt 2. Maybe we can look at this again in a Gantt chart form, and this is a little bit sloppy. So we have insert, we've got cut, and we have sew, right? And then we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So minute 1, minute 2, and minute 3. I can leave that. Whoops. Oh no. We have our first t-shirt goes in and it gets inserted for 3 minutes. Our second t-shirt then is cut for 3 minutes. And then we have 6 minutes of sewing. So here we see our flow time of 12 minutes. But we know that sew has to be working flat out all the time. So t-shirt 2 has to be ready in the system to be fed into sew as soon as t-shirt 1 is done. And this can continue on so that sew is always busy working for 6 minutes. And what we see here in the Gantt chart, in this 6-minute time period, which is what we're going to call the production cycle, that's given by our bottleneck here, we're going to have 1 t-shirt that is processed in that 6 minutes in insert and cut, and 1 t-shirt that is going to be processed in sew for a total of 2 minutes, 2 t-shirts. And this inventory, this 2 equals RT equals 2 t-shirts, is sometimes called the critical WIP. For a set flow rate or for a set throughput and for a given time, if we're below the critical WIP, then our bottleneck will not have enough to work on and will be idle sometimes, which is bad. And as we'll see next, any inventory above the critical WIP will cause the process flow time to increase.